Mosquito dey your window, you don't close your window. Mosquito dey your window, they poke your window. They poke your window. You they see the mosquito, right? You don't see the mosquito, no fit enter inside, no matter the amount of poking. So hi everyone, I promised you guys that my videos will be coming from 12 p.m. So I'm going to be answering this person. His name is at John Nsebot. I don't know that name, but at John Nsebot. And his question says, explain quantum tunneling to a layman. A layman, I should explain quantum tunneling. Please guys, do me a favor, follow anybody I pick. All the people that asked questions on this video are supporting this video. Please follow them massively, so that they can come back next time if we do something like this. So guys, it's Physics Friday. Let's go. So he said, explain quantum tunneling to a layman. First of all, have you ever thought of two things? Maybe you are playing a ball on a flat surface, right? There's a hill close to the flat surface. Let's just draw. This is the hill, and this is the flat surface. This is the ball, right? The person playing the ball, let's just say this is the person playing the ball, right? If you play this ball to this hill, there's a probability that this ball can get here, climb this place, and get to the top of the hill. And that probability is only when the energy in this ball overcomes that of the hill. It's greater than the height of the hill. From here to here is the height of the hill. So if this energy is greater than this height of energy E was greater than the height of the hill, then this ball will get here, hit here. Instead of returning back to the person who played it, right? It will just go and get to the top of the hill. That is our imagination. You know, I told you physicists are close to God and we are related to nature. But no, if the energy in this ball is less than that of the height of the hill, the ball will just get to this point, will not be able to climb because there's no energy to push it upwards. So it will go back to this guy here. Now, in quantum tunneling, they are telling us that we are not looking at the classical aspect of this. We don't care if this thing reaches here, it doesn't have the energy to climb here. They are telling us that if this ball reaches here, there is a little amount of wave emission that will pass through this and possibly reflect on top of the hill. Right? Now, quantum tunneling is practically telling us that a particle, or like this ball, is in two forms. You have the wave-like particle, and then you have the particle-like particle. Wave-like particle obeys the what? The quantum tunneling. That is what the quantum mechanics. And now it's telling us that there is a probability that there is a little decay from the particle and emission that will cross the height of the hill and get to the top, and that is the probability. Now, they said in quantum physics, we are dealing with probability of things to happen. Like when the sun emits around, we use what? The nuclear fusions. These are examples. Okay, let's use the physical, let's use the Nigerian analogy. Mosquito dey your window, you don't close your window. Mosquito dey your window, they poke your window. They poke your window. You they see the mosquito, right? You don't see the mosquito, no fit enter inside, no matter the amount of poking. But in quantum tunneling, because this guy talks, say make I explain them as or to a layman. But in quantum tunneling, they are telling us that there is a probability that as the mosquito is poking the window, there is a wave the mosquito has emitted, and then that wave will touch your skin. Say that mosquito go bite you from outside. That mosquito go bite you even when that mosquito no touch you. You see, safe physics, and this applies to real life experiment. So I hope I've been able to answer you. No, you know I don't do things without mathematical proof. Let's get to the mathematical proof. Now this energy is still valid. Okay, let me clean here. Let's take the particle. Particle to be the ball, the mass of the particle, and the energy in ball, the height of the wall, height of the hill, you know, A, which is what? The width. Look at the hill here. There is a width. There is an A here, the width. Now, if we want to bring this thing to the mathematical form, what we have to do is we are taking quantum tunneling T to be, we are dealing with scattering, we are dealing with decaying in quantum mechanics, we are dealing with probability. So we have to take the exponent. Exponent of minus 2k A. A is the what? A is the width. Now, if we're taking it, K has its own formula. K is equal to 2m, 2 of that mass, bracket, that's the height minus the energy over reduced Planck constant. This one, H here, is what? Now, V here is approximately the height, V naught. Then, let's just say H slash is what? The reduced Planck's constant. Now, this is the theoretical part of it. This is the particle. And then this is the mass of the particle. The energy. Now, look, there's a small postulate. If the height is greater than the energy, classically, probability of the ball to cross over will be 0. But if the energy is greater than the height, probability of the ball to get to the hill is not 0. It's close to 1. Going to 1. Approximately 1. Right? So, let the layman forget this part. I'll just take the other part. Thank you so much. Thank you at John Nessel Boat. Thank you. I appreciate.